Welcome back to the class on HVDC transmission system. In this lecture, we are going to compare the AC and DC transmission system. And finally, we are going to conclude when we can go for the HVDC transmission system. The comparison is made based upon the three parameters. One is economics of the transmission. Second one is the technical performance. And the third one is the reliability of the system. Based upon the three parameters, we are going to compare the AC transmission system as well as the DC transmission system. First, we are going to start with the economics of a transmission system. The economics of a power transmission system is broadly divided into two categories. One is root of way cost, nothing but to laying the transmission line, how much cost is required. The second one is the operational cost. Under the operational cost due to the loss which are occurs in a transmission line, that will be covered. When you come to the root of way cost, the different costs are available. When you are going to lay the transmission line, it requires a conductor. The same manner it requires a towers and terminal cost, and insulators and breakers. For given voltage rating and power level, the same type of insulators we can use, but in case of a DC transmission system, it requires two conductors, but in case of AC transmission system, it requires three conductors. So in a HVDC system, the number of conductors will be decreasing. And one more thing is, these conductors were keeping on the tower. So the strength of the towers also will be decreases in case of a HVDC system and compared to the AC transmission. The terminal cost will be very high in case of a HVDC system, because in HVDC system the converters are there, rectifier station as well as inverter station. Those stations are very costly because of the converters. When you come to the losses, in HVDC system there is no corona, because only the negative conductor we are using to transmit a power. The return path will be taken through the ground. So the corona loss will be very lesser in case of a HVDC system. Next, skin effect is also not there in case of a HVDC system. Due to that, the amount of power will be lost in a HVDC system will be lesser when compared to the AC transmission. But the only thing is that terminal cost will be very high in case of a HVDC system. In this diagram, if you observe, means on the x-axis we have taken the distance, on the y-axis we have taken the cost for the laying of AC transmission system or DC transmission system. This is the profile for the AC transmission system. This is the profile for the DC transmission system. This is the intersection point. This point is nothing but a break-even distance. If the length of the line is less than this break-even distance, then we have to go for the AC transmission system. The length of the line is more than the break-even distance, means it is better to go for the HVDC system for the economical point of view. Next, technical performance. In case of HVDC system, we can fastly control the power passing through the transmission line, but in case of AC transmission system, it is not possible. So in case of HVDC system, we can improve the transient and dynamic stability, and also we can control the fault current in case of HVDC system. Not only these parameters, some of the other parameters also will be improved in case of HVDC system when compared to the AC transmission system. Those parameters are stability limit. The second one is the voltage control, line compensation, AC interconnection and grounding. All these parameters will be improved in case of HVDC system compared to the AC transmission system. Now we are going to see one by one stability limit. In case of AC transmission system, this is the one bus, this is the second bus, this is the line. How much power is passing through the line is highly depending upon the angle between these two buses, V1 and V2, nothing but a delta. For given amount of power, this angle is depending upon the how much length of this line. As the length is increases, the angle also will be increases. So the amount of power passing through the power transmitted through the in AC transmission line is highly depending upon the angle, where it is highly depending upon the length of the line. But in case of HVDC system, It is not depending upon the length of the line. See, from this graph, if you observe, means on the x-axis we have taken the distance, on the y-axis we have taken the power. See, the DC, how much power you are passing through the DC line, that is constant, that is represented with the dotted line. But in case of AC transmission system, that is inversely proportional to the distance. As the distance is increases, the power transmitted through the line will be decreases. Voltage control. In case of AC transmission line, the voltage on a line is highly depending upon the line charging and voltage drop in a line. In case of AC line, there is some amount of capacitance will be existing between the conductor to conductor as well as conductor to the ground. Those capacitance will be taking a some amount of current. The current will be affecting the voltage on a line. Not only that, the line has a some amount of reactance. Because of the reactance, when current is passing through the line, the some amount of voltage will be dropping in the line also. That is also affecting the voltage available at a bus. Not only these two parameters, the voltage available at a bus in a AC transmission system is highly depending upon the surge impedance loading. The load on a line is equal to surge impedance loading, means the sending end voltage and midpoint voltage and receiving end voltage is same. Suppose the load on a line is greater than the surge impedance loading, means the voltage at midpoint will be decreases by keeping the sending end voltage and receiving end voltage is constant. Suppose the load on a line is less than the surge impedance loading, means the voltage at midpoint will be overshooted, but the sending end voltage and its receiving end voltage is kept constant. So from this analysis we can say very easily that the voltage profile across the line is highly depending upon the line charging current and voltage drop, and also depending upon the how much load we are keeping on the line. Suppose if you want to maintain the voltage at the two ends of a line is constant, means it requires the reactive power. So in case of AC transmission system, the line requires a reactive power to maintain the to transmit a power. But in case of DC transmission system, it does not require any reactive power to transmit a power from. In case of AC transmission system, suppose if you have wanted to transmit a power through the AC cable, it is creating a serious problem in case of AC transmission system. So that the break even distance is around 50 kilometers in case of a AC transmission system where we are using a cables. Line compensation. Already we have seen to maintain the voltage at a two ends same and midpoint is same, means it requires some amount of compensation to the AC transmission line. And to increase the power through the line, also it requires a reactive power compensation that we can meet by means of a static wear compensator or synchronous condenser. In case of DC line, it does not require any compensation of the reactive power for the transmission line, but for converter station, it requires a reactive power. That's the problem of AC interconnection. We have a two AC generation stations. This is one generation station, this is another generation station. We are connecting these two generation stations by means of tie line. So why we are going to connect by means of tie line, means suppose in one generation station it does not have that much of power, that we can take up by means of the another generation station through the tie line. That power adjustment we can make it by means of a tie line. But when you are going to interconnect the two generating stations by means of a tie line, how much power is passing through the tie line and frequency of that power, based upon the two parameters, we have to perfectly control the generation 1 as well as the generation 2. Even though if you are perfectly control the generations which are connected in a tie line, those are affected to the some of the problems which are due to the presence of large power oscillations in a tie line. It is going to affect the frequencies of any one generations, and number of faults which are occur with the tie line also will be increases. And third one is the if any disturbances occurs in a one system, that will be passes through the second system through the tie line. These are the some of the disadvantages with a AC interconnection system. Suppose if we go the two AC systems which are connected in a DC link means, due to the fast controlling of the power in a DC link, we can overcome all these problems. Ground impedance. Suppose if any fault is occurs in a AC transmission system, the zero sequence current is passing through the line. The ground impedance of the conductor is very higher. If that current is passing through the ground impedance, which is affecting the power which is passes through the line, and also affect the telephonic interference in case of AC system. But in case of DC system, the current is passing through the negative conductor and current will be returned to the ground. So there is a negligible amount of ground impedance for the line. In case of HVDC system, we are acting the two poles through the pipe. If that pipe is corroded due to the passing of the DC current, then the ground impedance in a HVDC system also will be higher. If you are properly maintained, the ground impedance in HVDC system will be negligible when compared to the AC transmission system. So with respect to the ground impedance, we can go for the HVDC system. In case of a HVDC system, the AC network is feeding a power to the DC converter through the balanced voltage and current. Due to any unbalance in a voltage at AC side, we can run the single pole DC link for some time. But in case of AC transmission system, if any unbalance occurs in any one phase means, we can't run the AC transmission system as a single pole just 1 second. Next, reliability. From the reliability point of view, in the world so many HVDC systems are there, so much of data is available. From that data, we can calculate the reliability statistics for the HVDC system. From that statistics, we can say very easily that HVDC system has a very good reliability when compared to the AC transmission system. The reliability of the SCR is good when compared to mercury arc rectifier. If any advances occurs in terms of device, control and production, it also will be improve the reliability of the HVDC system. The overall HVDC system reliability can be calculated by means of two parameters. One is energy availability and transient reliability. Now we are going to see what is meant by energy availability. Energy availability is defined as 1 minus equivalent outage time by total time into 100. Equivalent outage time is equal to the actual outage time into fraction of the system capacitance loss due to the outage. Next, transient reliability. The transient reliability we can calculate it 100 into number of times HVDC system performed as a design divided by the number of recordable AC faults. The recordable AC faults are those faults which are caused one or more AC bus phase voltage drop below the 90% of the voltage prior to the fault. There are some disadvantages with HVDC system. We know the HVDC system has a rectifier station as well as inverter station. Here control system is there, here transformer, here the supply. The cost of the stations will be very higher. I think the terminal cost of the HVDC system is very higher. In case of HVDC system, we are not able to use a transformer to increase the voltage higher and lower because we are transmitting a power at a DC level. Next, due to the operation of this converter, is generating a harmonics in the AC side as well as a DC side. It requires a very costly filter to filter out the harmonics. It also requires some amount of reactive power at a rectifier station, inverter station. How much reactive power is required means nearly 60% of the rated real power we are transferring through the rectifier station. It requires a reactive power at a rectifier station, but it does not require any reactive power at a lines. Next, it requires a very complex control system to control the rectifier station as well as inverter station for fast controlling of the power through the line. Thank you very much for watching this video.